Yeah. Now, it might be possible that you could invert from a two-dimensional to a one-dimensional, but not with a matrix. It's impossible. You can't go from one dimensions up to two dimensions, or you can't invert it. So the kind of idea, you've got a doubly infinite space here, sent to a singly infinite, you can't go backwards. So this thing is not invertible. This thing is definitely not invertible because loads of things are sent to a single thing. And so basically what I'm saying is if the determinant is 0, you cannot invert it, which we kind of saw a little bit earlier, right? So this is just showing another thing. So here you have, this is the same square, it actually gets sent to something like this, and the area of this you can show is AD minus BC, which is right down diagonals A by D, minus left down diagonals, like what we've seen before. Well, you've heard me say these things, and when I say that right down diagonal minus left down diagonal, that thing will pop up again in this chapter. So this is just showing, now we won't show that the area of this is AD minus BC, but you can do it. And that means that the determinant of this, the scale factor is AD minus BC, so the determinant of one of these is AD minus BC. Okay. Alright, so there's some kind of complicated stuff. Oh no, okay. So this here is the full definition, which is a little bit difficult, but basically says the determinant, blah blah blah. Well, we're only interested in 2 by 2 and 3 by 3. And they can both be summarized as right down diagonals minus left down diagonals. The determinant of a 2 by 2, which you write like this. This is just another way for writing down the determinant, so maybe we'll just make that explicit. Oh, it's written there. A with the bars is another notation for the determinant. And we remember it's a scale factor. And how do you do it? For a 2 by 2, it's right down diagonals minus left down diagonals. So just remember it's a scale factor. So you got this big theorem here. Now this is similar to what we saw earlier with the dot product equal to 0 is equivalent to two vectors being perpendicular. It's an if and only if statement. So it says here, if the determinant is non-zero, then it's invertible. If the determinant is 0, it's not invertible. It's not possible for a matrix to be invertible and for its determinant to be 0. That's not possible. And it's not possible for a determinant with a non-zero scale factor to not have an inverse. These things are exactly the same thing. These are the same and these are the same. If we just circle these. Maybe make a roundy circle this. And a square circle on the middle. A square circle, a square. So a square matrix is invertible if and only if the determinant is non-zero. So it's kind of two theorems. So this is something that I definitely can examine. I think as far as I remember, it is on your paper. It's a theory thing. You just have to kind of get your head around it. To me, like, how do I remember it? I remember it in terms of the scale factor. If the scale factor is 0, I get loads of stuff sent to tiny bits and I can't send back. If the determinant is non-zero, well, there's actually a formula, a very complicated formula, but there is a formula for the inverse that works. So I don't know how you get your head around this, but we'll put just, it is important. Because there's lots of things that I say and maybe they're not that important. This one is example. Okay. Right, so we'll look at...
Excuse me?
Yeah.
We'll say in the final exam, will we be asked stuff like theorems and stuff, or will we just...
So, well, you'll be asked to use them. So I'll give you, I think there's an example down there. We'll get some more. So see this question, This says, for what value to t, find the value to t for which this is equal to 0. This question could also be asked, for what value t is this matrix not invertible? So that's how it would be asked. There's another one, actually, if we go, I take your, just to see, the question is, how can I ask you questions about this in an exam? So on the next page, similarly, okay, no, that's a different one. If you go to page 92, question 2c, that could be done using this theorem. So the matrix of ones is invertible if you calculate the determinant, and you'll do 1 by 1 minus 1 by 1 is 0. So that means it's the determinant of 0 is not invertible. That's one way of doing that one. The other questions, we're looking to page, if you want to look at page 104, question 6. For what values of t, find the values of t for which this does not have an inverse. So you'd have to find, for what value of t, the determinant of that 3 by 3 is equal to 0. Similar question, I think, is on the next page, 105, question 9 and 10. Page 105, question 9, does it have an inverse? You calculate the determinant. If it's 0, it does not have an inverse. Similar story with question 10. What you do is you find the determinant in terms of k. Well, that's a different one. You'd have to show that the determinant of that is never 0. If you calculate the determinant, it will fall out in the wash. Now, we haven't set out to find the determinant of a 3 by 3 yet, so that's how it will be examined.
What I'm getting at is we won't be asked to define theorems, right?
To state them, no.
Oh,
Okay. Right. So this question, yeah, so it's said like this, this question could also be presented. For what value t is this matrix not invertible? So we find the determinant of the matrix, which is right down diagonals minus left down diagonals, and we're going to solve it equals 0. So the determinant of A equal to, so right down diagonals minus left down diagonals, so it'll be 1 by minus 6. That's the right down diagonals. Take away 3 plus t times 3t. So we'll multiply this out a little bit and see we get 1 by minus 6 is minus 6. And then, now I'll keep the minus there for a second. I have 3 by 3t, which is 9t. And t by 3t is what?
2t squared.
Spot on. And so we end up with minus 6 minus 9t minus 3t squared. That is the determinant of that matrix in terms of t. Right. Now we're interested in this equal to 0. Now the question says what is equal to 0? I'd probably more likely ask it like this. What value of t is this matrix not invertible? For it to be not invertible, the determinant is 0, so we solve this equal to 0. So we're looking at minus 9, was it? Minus 6, minus 9t, minus 3t squared equal to 0. Now, this is one of the places where I can go on a rant for 10 minutes, and I better not. In this module, you don't have to factorize quadratics. I probably haven't got an exam on the exam paper. It could come up in question in your second test. So if you got one of these equations with a t squared, a t, and a constant, this is a quadratic. And what you want to do is get it like, so kind of x squared, x, and a constant. I would say here, there's one obvious thing to do. What do you think would be an obvious thing to do here?
Divide by 3.
Divide by 3, or even better?
Minus 3.
Minus 3. So we'll divide both sides by minus 3. And I'm going to write it the square first, then the, what we call the linear term, and then the constant. So minus 3t squared divided by minus 3 is t squared. Minus 9t divided by minus 3 will be plus 3t. And minus 6 divided by minus 3 is equal to 2. Now, what I will say is that if you go to level 7, you need to be able to factorize these. Write them as like t plus something by t plus something. I don't really need that in this module. If this was if time wasn't of the essence, I would spend ages, or I'd spend more time doing this. In this module, it's not a concern. You've done this in the last module. Now, what that means is if you're confronted with this, you can factorize it, but you can definitely use the minus b formula. Now, have you any kind of a feeling? Would you prefer to factorize it or use this minus b formula? Where do you want to go from here? This may or may not be coming up in this module is what I'm saying. But it's something from the last module. Any feelings?
Suppose factorize it.
Factorize it, okay. Now if you say factorize it, I'm not going to spend loads of time on it. You can use the formula. I'm going to just go really quickly. I'm not going to explain what I'm doing totally. This is how I would factorize. So the way I factorize is you multiply the coefficient of the square by the constants, that's 1 by 2. And you get the number 2. You look at all the factors of 2, which is 1 by 2 and 2 by 1. Well, 1 by 2, there's no point going 2 by 1. I try and rewrite the middle term in terms of those. So I end up with t squared. I rewrite the 3t as 1t plus 2t. So as far as I'm concerned, if you can't follow this, it doesn't bother me for this module. This is how I recommend factorizing. Is there something common out of the first two? T. So I take out the t. And what am I left with? T plus 1. And can I take something out of the second 2 that leaves t plus 1 again? 2. What's common out of these two? T plus 1, so you can take that out as a common factor, t plus 1. And what are you left with? T plus 2. Did you do it like, you hardly did it like that last semester, did you? Okay. Well, that's how I recommend doing it. So that's factorizing. The big idea here, it's hard to say when a sum is 0. It's easy to say when things multiplied together are 0. If two things are multiplied together giving you 0, what can you say? So I've got number by number equal to 0. What can you say about the numbers?
One of them equals 0.
One of them has to equal 0. You could, plus plus gives you plus, minus minus gives you plus, minus plus gives you minus. The only way you end up with 0 is one of them is 0. So you have t plus 1 is equal to 0, or t plus 2 is equal to 0. Take away 1 from both sides, take away 2 from both sides, you end up, there's two values, minus 1 and minus 2. I'm not going to bother with this next one because I don't think it gives another quadratic, but I'm fairly sure I'm not going to examine the other quadratic. Okay. So that's the kind of question. So for ye, if it comes up in the exam, it'll be an easier equation. It'll just be like 2t plus 6 equals 0. Okay. Now, the next thing is, what about a determinant of a 3 by 3? Now, I could teach you how to calculate the determinant of a 4 by 4. I won't do that. I'll just show you how to do a 3 by 3, which is enough for this. If you really needed to calculate the determinant of a 4 by 4, there's online calculators to do that. Obviously, there's an online calculator for a 3 by 3 as well, but obviously we're going to ask you to do these. So you've actually seen this before. This is actually fine. This is the right down diagonals minus left down diagonals. So if you want to find the determinant of a 3 by 3 matrix, so you'd write the bars, signify you're interested in the determinants, and we say it's making up the numbers here: 3, 0, minus 2, 6, 1, 4, let's say 10, minus 1, 2. So if you're interested in the determinant of this, now what does that determinant mean? Well, a 3 by 3 matrix, it wouldn't be sending a 2-dimensional box to 2, 1 and 0 dimensional things. It would be sending a 3-dimensional box to 3, 2, 1 and 0 dimensional things. If it sends the 3-dimensional box to 3-dimensional box, this determinant will be non-zero and it will be invertible. If it sends the 3 dimensions to 2 or to 1 or to 0, it's not invertible, and what we get out here will be 0. In a certain sense, most matrices are invertible. So we've seen this before. Now there's no IJKs here, but it's the same kind of crack. You write the first 2 columns again. And then you do right down diagonals minus left down diagonals. So 3 by 1 by 2, 0 by 4 by 10, minus 2 by 6 by minus 1. To show that, again, this is the right formula, you can actually use vectors to do that, but just take my word for it, I suppose, what I'll say there. So 3 by 1 by 2 gives me 6. 0 by anything gives 0. Minus 2 by 6 is minus 12. By minus 1 is plus 12. That's the right down diagonals. Take away the left down diagonals. 0 by 6 by 2. 3 by 4 by minus 1. Minus 2 by 1 by 0. So the 0 by anything gives 0. 3 by 4 is 12. By minus 1 is minus 12. And finally, minus 2 by 1 is minus 2, by 10 is minus 20. And I think we end up with, this looks like 18 minus minus, which is plus 18 plus 32, which is 50. So what that means is that the matrix is invertible. I'll just write this down, not 0. So the matrix 3, 0, minus 2, 6, 1, 4, 10, minus 1, 2 is invertible. If it was non-zero, you could say that, if it was 0, you could say it's not invertible. And that it's 50 means that the volume is multiplied by 50, which means actually that you can go, we won't go into too much, but like say if you take an original volume of 1, so if you took this, take all those points, maybe just the corner points, so like there'd be like there'd be 8 of them, there'd be 1 or 0, 0, 0, 1, 0, 0, 1, 1, there's 8 of them, and send them, you get another shape. It'll be a weird kind of a shape. Let's just say it's another box, but it'll be a bit bigger. It'll be all kind of deformed, not badly, just the straight bits will be straight bits, but after that. And the volume of this will be 50, which means that roughly, I think these will get multiplied roughly on average by about 3.6. 3.6 by 3.6 by 3.6 is about 50. And you should see roughly the 3.6 kind of, well, you can't see it, but somehow it's in there. Yeah. Okay. Okay, so this is what an exam question would look like. One that I would give you. For what values of k does the matrix below not have an inverse? So you got to get it straight. So if the determinant is 0, that corresponds to maybe this box being sent into a two-dimensional shape, and you can't go from two-dimensional back to three-dimensional. So the scale factor here, say if this is matrix M1, the determinant of M1 is equal to 0. So for it not to have an inverse, the determinant of this must be 0. We have the theorem that a matrix is invertible if and only if its determinant is non-zero. Therefore, the matrix is not invertible if and only if the determinant is 0. So we calculate the determinant. So we can write this as maybe A with the bars. So I think what I'm saying is most matrices have inverses, like there's infinitely many values of k. I think only one of them doesn't give you an invertible matrix. So it's kind of rare for them not to be invertible. So again, we write the first two columns. No ijk's knocking around here.